Between the constellations, vast stretches of pure darkness swallow the light. These are the starless regions of space, immense voids that defy everything we thought we knew about the cosmos. By the end of this journey, you will see the universe in a completely new way, uncovering the hidden forces and mysterious objects that dwell in these cosmic shadows. What if these empty spaces hold the key to understanding dark matter, or even stranger, doorways to other realities? How much of the universe is hiding in plain sight, just beyond what our eyes can see? These voids are not simply empty space between galaxies. They are immense structural features of the universe itself, vast bubbles in the cosmic foam where the density of matter plummets to almost nothing. To call them empty, however, is a profound misunderstanding. While they may be devoid of the bright, shining galaxies we are used to seeing, they are far from inactive. Scientists refer to these areas as cosmic voids, and their existence forces us to reconsider what we mean by nothingness. They are not a blank slate, but a critical component of the universe's large-scale architecture. Picture the universe as a colossal sponge. The gleaming filaments and clusters of galaxies are the solid material, and these immense, dark voids are the holes. Their sheer size is almost impossible to grasp. One of the largest known, the Boötes Void, stretches an astonishing 330 million light-years across. If our solar system were placed at its center, we would have had no idea other galaxies even existed until the mid-1960s. The emptiness is so profound that it challenges our very understanding of how the universe formed. How could gravity, which pulls matter together, have left such gargantuan pockets of nothing? The prevailing theory points to the very beginning of everything. Tiny quantum fluctuations in the early universe were stretched to enormous sizes during a period of rapid expansion called inflation. These ripples in spacetime became the blueprint for all structure. The densest regions collapsed into the galaxies and clusters we see, while the least dense regions expanded and emptied out, becoming the voids we observe today. But this emptiness is dynamic. The gravitational pull of the dense walls of the void actually exerts a force on the galaxies near its edge, subtly influencing their motion. Furthermore, the expansion of space itself happens just a little bit faster inside these empty regions, a subtle clue to the mysterious force we call dark energy. So these voids are not just passive absences, they are active players shaping the cosmos through their overwhelming lack of substance. The gravity we feel from stars and planets is not enough to hold the universe together. Something else, something invisible, is providing the extra pull. This is dark matter, the unseen architect of the cosmos. It is the hidden framework upon which the entire visible universe is built. Think of it as the cosmic skeleton, an invisible structure that dictates where galaxies can form, and just as importantly, where they cannot. In the dense regions between voids, dark matter clumps together, its gravitational pull acting as a trap for the gas that eventually forms stars and galaxies. But inside the vast starless voids, this scaffolding is almost absent. The distribution of dark matter is incredibly sparse, which is why so few galaxies have managed to coalesce there. The void itself is a monument to a profound lack of this mysterious substance. Our understanding of dark matter's dominance began with the work of astronomers like Dr. Vera Rubin. By studying the rotation of galaxies, she found that stars on the outer edges were moving just as fast as those near the center. According to the laws of gravity, these stars should have been flung out into space unless some invisible mass was holding them in, providing extra gravitational glue. This was the first strong evidence that the universe contains far more matter than we can see. We now believe this dark matter makes up about 27% of everything in the cosmos. Yet, after decades of searching, we still have no idea what it is made of. It does not emit, absorb, or reflect any light, making it completely transparent. We only know it is there because of its gravitational influence. This leads to a fascinating question about the voids. Could peculiar behaviors of dark matter be responsible for their existence? Perhaps dark matter particles interact with each other in ways we have not yet discovered, creating pressure or flows that push normal matter out of these regions, sculpting the immense emptiness. To truly understand the shadows between the stars, we must first decipher the nature of the invisible force that shapes them. This relentless expansion is fueled by the universe's greatest mystery, dark energy. While dark matter pulls the cosmos together, dark energy is the invisible force relentlessly tearing it apart, accelerating the expansion of space itself. It was discovered quite by accident in the late 1990s, when two separate teams of astronomers were observing distant stellar explosions called Type 1, a supernova. They expected to find the expansion of the universe was slowing down due to the pull of gravity. Instead, they found the opposite. The expansion was speeding up, as if some unknown repulsive force was overpowering gravity itself. This shocking revelation earned them the Nobel Prize and completely rewrote our understanding of cosmic fate. We now believe this dark energy makes up about 68% of the entire universe. Its effect is felt everywhere, but it is within the vast cosmic voids where its power is most absolute. With so little matter inside these regions to provide any counteracting gravitational pull, dark energy operates unchecked. It stretches the emptiness itself, making these already immense voids grow even larger over billions of years. This is not a gentle process. It is a fundamental force reshaping the architecture of the cosmos, relentlessly pushing the walls of these voids further apart and deepening the shadows between the galaxies. This has profound implications for the ultimate fate of everything. If dark energy continues to dominate, the expansion will continue to accelerate forever. Galaxies will be pulled so far apart that their light can never reach each other, and the universe will end not in fire, but in a cold, dark, and lonely isolation, a scenario cosmologists call the Big Freeze. But to truly understand the voids, we must ask a deeper question. Could dark energy behave differently inside these profound emptinesses than it does elsewhere in the universe? What if the properties of this mysterious force are not constant, but change depending on the density of its surroundings? The answer could rewrite physics itself, beckoning us to probe these cosmic shadows for clues to the true nature of reality. The Boötes Void is a monument to cosmic emptiness, a void so vast it defies simple explanation. Discovered in the early 1980s, this region of space is a true desert, spanning an almost unimaginable 330 million light-years. Yet within this colossal volume, astronomers have found only a tiny handful of galaxies. If our own Milky Way were adrift in this nothingness, the nearest major galaxy would be millions of light-years away, leaving our night sky almost completely black. This profound emptiness earned it a dramatic nickname, the Great Nothing, and it presents a direct challenge to our models of how the universe organizes itself. How could a region so large contain almost nothing? Astronomer Robert Kirshner and his team were among the first to study its peculiar structure, and they found it to be far emptier than anyone had predicted. It was not just a sparse area, it was a genuine vacuum, a hole in the cosmic distribution of matter. This forces us to ask what process could have scoured this region so clean. One leading theory suggests it is not one void, but many. The Boötes Void might be the result of smaller voids merging together over billions of years, like soap bubbles combining to form one giant cavity. Their walls dissolved, leaving behind this single, staggering expanse of nothing. But other, more exotic ideas have been proposed. Could unknown physical forces or energies be at work within its boundaries, actively preventing matter from coalescing into galaxies? Are there strange, undiscovered objects lurking within its darkness, objects that do not emit any light we can currently detect? The Boötes Void stands as the ultimate example, a prime laboratory for studying the limits of our knowledge. It is not merely an absence of stars, it is an active puzzle, a profound mystery written in negative space, and it hints that the deepest secrets of the cosmos are hiding in its darkest corners. But even the profound emptiness of the Boötes Void may not be the strangest structure hiding in the darkness. Drifting through the constellation Eridanus is a different kind of cosmic anomaly, a place where the very background temperature of the universe seems to drop. This is the Eridanus Supervoid, and its existence is tied to one of the most perplexing mysteries in modern cosmology, a mysterious cold spot in the ancient light left over from the Big Bang. This light, known as the cosmic microwave background, is the faint afterglow of creation, a nearly uniform blanket of radiation that fills every corner of space. But in this one region of the sky, that background is noticeably, inexplicably colder. When the European Space Agency's Planck satellite mapped this radiation in exquisite detail, it confirmed the cold spot was real, a genuine anomaly that required an explanation. The most straightforward theory points directly to the Eridanus Supervoid. The idea is that as light particles called photons travel across a vast void, they must climb out of its gravitational well. Because the void has less matter, its gravitational pull is weaker than the surrounding regions. This means the photons lose more energy climbing out than they gain entering. And since a loss of energy for a photon corresponds to a longer wavelength, which we perceive as a lower temperature, the light appears colder after its journey. It is a subtle but measurable effect, like a marathon runner arriving exhausted after running uphill for 1 billion years. But here is the problem. The Eridanus Supervoid, while massive, does not appear to be nearly large enough or empty enough to account for the entire temperature drop observed. The numbers simply do not add up. This discrepancy has led some scientists to propose far more radical ideas. Could the cold spot be evidence of a collision with another universe, a bruise left on our cosmos from a primordial impact with a bubble universe in the multiverse? It sounds like science fiction, but it is a serious, if highly speculative, cosmological hypothesis. The debate is fierce, with each new observation scrutinized by both sides. This is the true power of these starless regions. They are not just empty spaces. They are cosmic laboratories, natural experiments that push our theories to the breaking point and force us to ask questions we never thought possible. What if the ultimate discovery within these shadows is not a new object, but a crack in the fabric of our reality, a fleeting glimpse into the infinite possibilities of the multiverse? Yet even in the profound emptiness of the Boötes Void, a few isolated points of light stubbornly persist. These are the loner galaxies, cosmic hermits adrift in an ocean of nothingness. The most famous of these is a spiral galaxy known as MCG plus 01020015, which astronomers have poetically dubbed the loneliest galaxy in the universe. It is so profoundly isolated that its nearest galactic neighbor is over 1 million light-years away. If you could stand on a planet within this galaxy and look out, the night sky would be a chilling, almost perfect blackness, punctuated only by its own stars. There are no nearby galaxies to provide a soft glow, no majestic Andromeda to grace the horizon. it is a single, solitary island in the vast cosmic sea. How did a galaxy form in such complete and utter isolation? Typically, galaxies are born and evolve through constant interactions, collisions, and mergers with their neighbors. These violent encounters trigger massive waves of new star formation, shaping a galaxy's destiny. But a loner galaxy like this one has never experienced such an event. It has grown up alone, its entire history dictated solely by the slow, internal processes of the gas and dust within it. This makes it a pristine laboratory for astronomers. By studying it, they can see what a galaxy looks like when it evolves in a near-perfect vacuum, untouched by the chaos that defines most of galactic life. The stars within it tend to be older and quieter, with fewer of the massive, short-lived blue stars that signify recent violent births. The galaxy itself is often anemic, its resources for creating new stars slowly depleting without any fresh material from outside. This raises a fascinating question about the potential for life. Could planets orbiting stars in such a lonely galaxy develop in a uniquely peaceful environment, free from the sterilizing radiation of frequent supernovae that plague more crowded galactic neighborhoods? Or is it a cosmic dead end, a place where the engine of star formation has sputtered out, leaving behind a dim, aging population of stars destined to fade slowly into the eternal dark? The existence of these loners forces us to reconsider the very definition of a galaxy, and reminds us that even the deepest voids hold singular, surprising treasures for those who know how to look. But the loneliest galaxy is not the only wanderer in the dark. Drifting unseen through these immense voids are entire worlds that have never known the warmth of a sun. These are rogue planets, celestial nomads untethered from any star, and they could be one of the most common yet hidden populations in the entire cosmos. A planet becomes rogue in one of two ways. It can form on its own from a tiny, collapsing cloud of gas and dust, a failed star that never gathered enough mass to ignite. Or, more violently, it can be gravitationally slingshotted out of its native solar system during the chaotic planetary billiards of its youth, cast adrift into the interstellar abyss. In the crowded galactic disk, such ejections are common, but in the profound emptiness of a cosmic void, these planets are truly on their own, destined to wander the eternal night. Billions, perhaps even trillions of these dark worlds could be silently moving through the galaxy. Their surfaces would be landscapes of absolute deep freeze, where temperatures hover just a few degrees above absolute zero. Any atmosphere would likely have long ago collapsed into a frozen crust, and the concept of a day or a year would be meaningless in the endless, starless dark. Yet, this does not necessarily mean they are dead. Scientists speculate that some of these rogue planets, particularly larger ones similar to Jupiter or Neptune, might retain enough internal heat from their formation to support vast, global oceans of liquid water deep beneath their icy surfaces. On Earth, we find life thriving in the most extreme environments, from volcanic vents at the bottom of the ocean to buried Antarctic lakes. Could similar biospheres exist in the lightless oceans of a rogue planet, sustained not by sunlight but by geothermal energy and exotic chemistry? The possibility, however remote, forces us to expand our definition of a habitable world. The greatest challenge is finding them. A rogue planet emits no light of its own and reflects no starlight. It is a nearly perfect black bullet speeding through the void. Our only hope of detection is a rare event called gravitational microlensing, where the planet's gravity briefly acts like a magnifying glass, distorting and amplifying the light from a far more distant star behind it. This fleeting signal is incredibly difficult to capture, but the next generation of powerful telescopes, like the Nancy Grace Roman Space Telescope, is designed to hunt for these exact signatures. What if the census eventually reveals that these lonely wanderers outnumber all the stars in the galaxy? This staggering idea would completely transform our understanding of these cosmic shadows. The voids would no longer be seen as empty deserts, but as unseen oceans teeming with hidden worlds. But what if the voids are not truly empty, but instead filled with countless invisible anchors? Among the most compelling and elusive candidates for dark matter are primordial black holes. These are not the black holes we know, the kind formed from the dramatic collapse of a massive star. Primordial black holes are something else entirely, hypothetical relics from the universe's explosive first moments. Theorists suggest that in the extreme density and turbulence following the Big Bang, random fluctuations could have collapsed directly into black holes. Their sizes would not be dictated by a star's mass, but by the random chance of those initial conditions. They could be as small as an atom or as large as an asteroid, all of them packing immense mass into a tiny, invisible point. A black hole the mass of a mountain could be smaller than a grain of sand, yet its gravitational pull would be unmistakable. This is where the cosmic shadows come in. These ancient objects would be nearly impossible to detect directly, as their small size means they emit virtually no Hawking radiation. But their collective gravity could be the hidden mass that subtly influences the motion of the few galaxies within a void, or helps sculpt the void's very shape. Finding one would be a monumental challenge. Astronomers would have to rely on a phenomenon called microlensing, watching for the telltale flicker as a primordial black hole passes in front of a distant star, its gravity bending and briefly magnifying the starlight. A successful detection would do more than just solve the dark matter puzzle. It would provide a direct window into the universe's first second, a time otherwise completely inaccessible to us. These black holes would be frozen fossils, carrying information about the conditions of creation itself. Their existence would forge a profound link between the world of the very small, particle physics, and the very large, the structure of the cosmos. The deepest voids may be the perfect hiding place for these ancient ghosts, their immense emptiness providing a clean backdrop against which we might finally spot the subtle distortion of a hidden world. Are the answers to our oldest questions not written in the stars, but locked within the event horizons of the universe's first and most secret inhabitants? Yet even these dark wanderers might be part of a far grander and more mysterious motion. Across the cosmos, entire clusters of galaxies are drifting in a coordinated, peculiar way, as if caught in a cosmic river flowing toward an unseen horizon. Astronomers call this phenomenon dark flow, and it is one of the most perplexing mysteries in all of cosmology. It was first identified by a team led by Alexander Kashlinsky, who meticulously mapped the motion of massive galaxy clusters by studying the subtle distortions they imprint on the cosmic microwave background. Their findings were startling. These clusters are not just moving with the general expansion of the universe. They are all streaming in the same direction at incredible speeds, over 2 million miles per hour, toward a single point in space, pulled by something immense that lies far beyond the edge of everything we can observe. This should not be possible. The gravitational pull of all the known matter in the observable universe should be uniform with no preferred direction. There is nothing on our maps large enough to exert such a profound and coordinated pull. So what could possibly be tugging on thousands of galaxies from beyond the veil of the known cosmos? One radical theory suggests that the colossal gravitational influence of another universe, a separate bubble in the multiverse, is exerting a pull on our own. Another idea points to a primordial irregularity, a flaw in the fabric of spacetime from the instant of the Big Bang, that set this entire cosmic current in motion. And this is where the voids re-enter the story. These vast, empty regions with their incredibly sparse matter might act as cosmic channels. With so little gravitational friction to slow it down, the dark flow could be more easily detected, and its effects more pronounced within these profound emptinesses. They could be the clearest windows we have into this mysterious current, the quiet rivers where the subtle tug of the unknown becomes just barely perceptible. This forces a breathtaking reconsideration of our place in existence. The observable universe, all 9 billion light-years we can see, might be just a small part of a much larger, grander structure. We are not just living in a cosmos, we might be living in a multiverse, and the starless voids could be our first hint of the shorelines of other realities. What if the ultimate pull is not from a thing but from a place we cannot see and may never be able to reach, but whose gravity we can feel in the silent, coordinated drift of the galaxies? Even the matter we think we understand is playing a game of cosmic hide and seek. Our most precise calculations of the universe's composition, based on the afterglow of the Big Bang, tell us exactly how much normal matter should exist. This is baryonic matter, the protons and neutrons that make up everything we can see, from stars and planets to our own bodies. Yet when astronomers add up all the visible material in galaxies, stars, and gas clouds, a staggering 30 to 40% of this ordinary matter is simply missing. It is a fundamental accounting error on a universal scale known as the missing baryon problem. So where did it all go? The answer may be hidden within the very voids we have been exploring. The leading theory suggests this missing matter is not gathered in bright, dense clumps, but instead has been stretched into an incredibly thin, hot web of gas that fills the spaces between galaxies and threads through the cosmic voids. Scientists call this the warm-hot intergalactic medium, a soup of matter so diffuse that it is almost a perfect vacuum by Earth standards. Yet it is so hot that it glows not in visible light, but in low-energy X-rays that are incredibly difficult to detect with our current telescopes. In the profound emptiness of a void, this gas could be spread so astonishingly thin that it becomes virtually transparent, a ghostly haze that slips through the nets of our observations. Finding it requires a new generation of space-based observatories, like the upcoming Athena X-ray telescope, which will act as a cosmic fishing net designed to trawl these dark seas for the faintest X-ray glow. Mapping this tenuous medium would do more than just balance the universe's books. It would reveal the final component of the cosmic web, the delicate filaments of gas that connect all structures together. This hidden reservoir is the universe's backbone, and by finding it, we complete our picture of where all the ordinary stuff of creation has been hiding, proving once again that the darkest voids are not empty, but filled with secrets waiting for the right light to reveal them. But the universe's deepest emptiness might be its most active place on the smallest scales. Within the profound vacuum of these cosmic voids, the very concept of nothingness breaks down completely. Quantum mechanics reveals that empty space is not truly empty. Instead, it is a seething, bubbling sea of energy known as the quantum foam. At this unimaginably tiny scale, pairs of virtual particles spontaneously burst into existence, borrowing energy from the vacuum before almost instantly annihilating each other and returning that energy. This frantic activity happens everywhere, all the time, but in the dense environments of galaxies and solar systems, its effects are completely drowned out by the overwhelming presence of matter and energy. However, in the near-perfect vacuum of a cosmic void, where the density of matter is almost zero, some scientists speculate that these quantum effects could be amplified. Could the relentless creation and destruction of virtual particles produce subtle energy fluctuations that we might one day detect? Could the quantum foam even influence the force of gravity itself in these sparse regions, creating tiny, measurable anomalies that deviate from Einstein's predictions? This is where the two most successful yet incompatible theories in physics, quantum mechanics and general relativity, might finally find a meeting ground. The void's incredible emptiness provides a unique laboratory, a clean room where the faint whispers of quantum gravity could be heard without the deafening roar of stars and planets. What if the key to unifying physics, to understanding the fabric of spacetime itself, is not hidden in the bright centers of galaxies, but in the deepest, darkest voids? The darkness is not a void but a vacuum, and a vacuum is far from simple. It is alive with transient energy, a quantum carnival happening in the shadows, and it challenges our most basic assumption that to see the universe's secrets, we must look for the light. These immense cosmic bubbles are born from the faintest whispers of imperfection. In the first fleeting moments after the Big Bang, the universe was not perfectly smooth. Tiny quantum fluctuations, smaller than a single atom, created a faint fingerprint of slightly denser and slightly less dense regions imprinted on the newborn cosmos. Then inflation struck. This period of unimaginably rapid expansion stretched these tiny ripples in spacetime to astronomical sizes, turning a microscopic tapestry into the cosmic blueprint for all future structure. The densest regions became the seeds for galaxies and clusters, while the least dense regions were the destined to be voids. Gravity then took over, acting as the universe's great sculptor. Over billions of years, matter steadily drained away from these underdense areas, flowing toward the gravitational pull of the denser peaks. The voids expanded, not because they were pushing matter out, but because everything around them was being pulled away. This process is dramatically accelerated by the mysterious force of dark energy. In regions already so empty, where gravity's pull is weakest, dark energy's repulsive effect operates with minimal opposition, stretching these voids even larger and accelerating their growth. Our best model for understanding this entire process is known as the Lambda cold dark matter model. Lambda represents dark energy, and cold dark matter is the invisible scaffolding. This framework allows cosmologists to run incredibly complex supercomputer simulations that trace the evolution of the universe from its first moments to the present day. When we look at these simulations, we see a cosmic web emerge that looks remarkably like the one we observe, complete with vast, interconnected voids. But the universe is full of surprises. While the simulations predict voids, they sometimes struggle to account for the sheer scale of a structure like the Boötes Void. Its immense size and profound emptiness are a challenge to the model, a puzzle that forces scientists to ask if they are missing a piece of the physics. Perhaps dark matter behaves in a more complex way inside these regions, or maybe dark energy's strength has changed over time. Every mismatch between the model and the observation is not a failure, but a clue. It is an opportunity to refine our understanding, to tweak the parameters, and to get closer to a true theory of everything. The voids are the ultimate testing ground for our cosmic blueprint, and with each new discovery, we are invited to redraw the map. This profound darkness that defines the voids is precisely what makes them so difficult to study. How do you observe an absence? Astronomers cannot simply point a telescope at a patch of black sky and see the void itself. Instead, they must map its invisible borders by meticulously cataloging the few galaxies that do exist, painstakingly tracing the outline of the emptiness by the sparse points of light at its edges. This is a monumental task requiring vast sky surveys that can take years to complete. Even then, the map is incomplete, showing only the luminous matter and missing the hidden components like the warm, hot intergalactic medium or any rogue planets drifting in the dark. The faint signals from these tenuous features are drowned out by the brilliant glow of nearby galaxies and the atmospheric interference of our own planet. To overcome this, science must move into space. Instruments like the James Webb Space Telescope with its infrared eyes and future observatories like the Athena X-ray telescope are our best hope. They are designed to detect the incredibly subtle whispers of energy that emanate from these regions, the faint X-ray glow of superheated gas or the subtle distortion of light from a rogue planet's gravity. But the challenges are not just technological, they are also physical. The sheer scale of a void means that any process happening within it unfolds over timescales that dwarf human history. We are capturing a single, frozen frame of a billion-year movie. Yet, the very difficulty of the task is what drives innovation. The need to see into the dark forces us to build better detectors, design more sensitive telescopes, and create more sophisticated computer models. The quest to understand nothingness is, ironically, fueling some of the brightest discoveries in astronomy, pushing the limits of what we believe is possible to observe and reminding us that the greatest secrets often require the most persistent search. These immense cosmic bubbles are integral to the very architecture of everything we see. They are not flaws or errors in the cosmic design, but essential components of a vast, interconnected structure known as the cosmic web. Picture the universe as a magnificent, three-dimensional tapestry woven from threads of dark matter and illuminated by galaxies. The brightest, densest knots where these threads intersect are the massive galaxy clusters. The threads themselves are the long, winding filaments of galaxies, and the voids, these great starless regions, are the immense dark spaces in between. They are the negative space that gives the entire web its form and definition. In fact, these voids make up the overwhelming majority of the universe's volume, a staggering 80% of all space. This means that if you were to randomly pick a point anywhere in the cosmos, you are overwhelmingly likely to find yourself in a void, adrift in a sea of near nothingness. Their arrangement is not random chaos. It is a fossil record, a preserved imprint of the universe's earliest moments. The specific sizes and distribution of these voids tell a precise story. They hold clues about the strength of dark energy, as its repulsive force causes voids to grow larger over time, stretching their boundaries and thinning out their already sparse interiors. They also reveal the nature of dark matter, as this invisible scaffolding dictated where voids could form in the first place. By meticulously mapping the cosmic web and measuring the voids within it, cosmologists are essentially taking the universe's vital signs. They can trace the entire history of cosmic expansion, from the inflationary burst at the beginning to the accelerated pushing of today. This perspective forces a complete shift in how we view these dark regions. Emptiness is not an absence, it is a fundamental and active part of the cosmic tapestry, its overwhelming presence silently shaping the destiny of all the bright, shining structures that surround it. This next leap into the cosmic dark will be guided by a new generation of eyes. The European Space Agency's Euclid Telescope and NAS, a forthcoming Nancy Grace Roman Space Telescope, are not merely upgrades. They are revolutionary instruments designed to do what has never been done before: map the void. Their mission is to stare into these immense nothingnesses and see not emptiness, but the subtle fingerprints of gravity and hidden mass. They will employ a technique called weak gravitational lensing, measuring the incredibly slight way the gravity of invisible matter warps the light from distant galaxies behind the void. It is like watching the subtle distortion of a landscape through a perfectly smooth yet warped pane of glass. By tracking this distortion across the vast expanse of a void, these telescopes can literally chart the distribution of dark matter within it, revealing its hidden skeleton. Simultaneously, their deep field surveys will catalog every single galaxy with unprecedented precision. drawing the definitive map of the void's borders and its few, lonely inhabitants. The sheer volume of data will be staggering, far too much for any human team to process. This is where machine learning enters the story. Advanced algorithms will sift through this cosmic haystack, searching for the needle of a strange pattern, an anomalous distribution of matter, or a gravitational signal that does not fit our current models. They could find faint clumps of dark matter drifting in the void, or perhaps something entirely unexpected, a signature of physics beyond our current understanding. Will the data finally reveal the true nature of dark energy by showing exactly how it stretches these voids over time? Could it even identify the faint, collective gravity of countless rogue planets or the subtle shimmer of that missing hot gas? The next decade promises to transform these cosmic shadows from abstract mysteries into detailed maps, turning our greatest questions into tangible data. The journey into the void is just beginning, and the discoveries waiting in the dark have the power to rewrite our story of the universe. The most profound emptiness might be a bridge to another reality. Some of the most daring theories in cosmology propose that these cosmic voids are not just empty space, but potential points of contact with other universes. This idea emerges from the edges of our understanding, from models like string theory, which suggests our universe is a three-dimensional membrane or brain floating in a higher dimensional space. In this view, a cosmic void could be a region where our brain curves or weakens, bringing it closer to another. A collision or a quantum tunneling effect between these brains could theoretically occur there, in the emptiest places where the fabric of our own reality is at its most thin and subtle. While entirely speculative, this concept offers a potential explanation for the most puzzling anomalies. Could the strange temperature fluctuations of the Eridanus Cold Spot be the gravitational echo of such a collision, a bruise left from a brush with a neighboring cosmos? Might the inexplicable dark flow be the pull of a massive structure in a completely separate universe, its gravity somehow leaking into our own? If this is true, these voids could exhibit bizarre properties, like faint energy signatures or localized shifts in the fundamental constants of nature, places where the rules of physics as we know them begin to bend. Proving it is another matter entirely. Such effects would be incredibly subtle, hidden within the noise of the cosmic microwave background or the peculiar motions of distant galaxies. The search is for a whisper within a whisper, yet the mere possibility transforms these voids from mere absences into the most thrilling of frontiers. They become potential windows not just into the darkness of our universe, but into the infinite light of others. What if the ultimate discovery within the void is not a hidden object but a doorway? Their evolution is a slow cosmic dance spanning billions of years. In the universe's youth, shortly after the Big Bang, these voids were far different from the immense emptiness we see today. They were smaller pockets, regions that were only slightly less dense than their surroundings. They were not truly empty, but rather, they were the seeds of the profound nothingness to come. As the cosmos aged, gravity acted as the great organizer of matter. It pulled the gas and dark matter from these underdense regions, channeling it relentlessly toward the growing filaments and clusters of the cosmic web. This process is called void emptying. It is not a violent expulsion, but a gradual gravitational drainage, like water slowly seeping from a sponge. As matter left, the voids naturally grew larger, their boundaries expanding outward. But this growth was given a powerful and mysterious boost by dark energy. In these already sparse regions, where gravity's pull is weakest, dark energy's repulsive force operates with almost no opposition. It stretches the very fabric of space within the void itself, accelerating its expansion and pushing its walls even further apart. This means a void today is not only larger than its ancient counterpart, but it is also far emptier, a more perfect vacuum. By studying this growth, cosmologists can read the history of the universe's expansion encoded in the sizes of voids from different eras. They act as cosmic clocks and measuring tapes. A population of older, smaller voids tells a story of a younger cosmos where gravity was still the dominant force shaping large-scale structure. The newer, gigantic voids reveal the era where dark energy took over, beginning its relentless campaign to push everything apart. This evolution points toward a startling future. If dark energy continues to dominate, these voids will keep growing. They will merge with one another, creating ever larger supervoids. The cosmic web, the beautiful tapestry of galaxies, will be stretched and thinned. The bright nodes and filaments will become isolated islands in an ever-deepening sea of darkness. The fate of the cosmos may be written in this gradual fading, the story of how the universe's vast emptiness grew from a whisper to a roar, eventually becoming the dominant feature of all existence. This profound cosmic emptiness forces a question that transcends astronomy. What is the true nature of nothingness, and what does our existence mean within a universe defined by it? We are conditioned to find meaning in presence, in matter, in light. We build our stories around the solid and the seen, yet the overwhelming evidence of the cosmos reveals a startling truth. The universe is not a collection of things, but a sea of absence punctuated by rare, temporary islands of something. We are the exception, not the rule. Our planet, our solar system, our galaxy, all exist in a relatively dense neighborhood, a bright filament in the cosmic web. But step outside that web into the void, and you find the universe's default state. A cold, dark, and near-perfect vacuum. This realization is deeply humbling. It challenges our innate sense of centrality and importance. The astronomer Carl Sagan captured this feeling perfectly when he described our world as a pale blue dot, a mote of dust suspended in a sunbeam. That perspective was born from looking out at the vastness, but looking into the voids gives us a different, perhaps even more powerful view. It is not just that we are small, but that we are surrounded by an immense and active nothingness. This is not a nihilistic thought, but an inspiring one. It means that life, consciousness, and our drive to understand are not inevitable products of a universe overflowing with matter. We are a rare and fragile spark in an infinite night. This shifts the question from why are we here to how is it that we are here at all. The existence of these voids makes our presence seem more precious, more statistically miraculous, and more worthy of protection. They teach us that the universe does not owe us meaning. We must create it ourselves through connection, through curiosity, and through the sheer act of looking into the dark and deciding to search for answers. Our journey into these shadows, then, is more than a scientific pursuit. It is the universe becoming aware of itself, a small part of the whole gazing back into the immense emptiness from which it came and asking, what else is out there? Humanity has always projected its deepest fears and boldest dreams onto the blank canvas of the night sky. These starless voids, in particular, have become a powerful symbol in our stories, a place where science fiction dares to fill the emptiness with meaning. In literature, from James Blish's novel Void to the treacherous traversals in Frank Herbert's Dune, these regions are often depicted as perilous deserts where ships can be lost for eternity, their crews succumbing to a profound existential dread. The void becomes the ultimate antagonist, a manifestation of pure isolation and the unknown. It taps into a primal fear, the terror of being truly alone in an unimaginably vast and indifferent cosmos. Yet, these same stories often flip the script, imagining these emptinesses not as ends, but as beginnings. They are portrayed as secret gateways to other dimensions, cosmic shortcuts hidden in plain sight, or the dwelling places of ancient, unknowable intelligences that prefer the quiet. This duality reflects our own complex relationship with the unknown. We are simultaneously terrified of it and irresistibly drawn to it. Our fictional portrayals ask a compelling question. Are we merely projecting our own anxieties onto the darkness, or is our storytelling instinct picking up on a deeper truth, a sense that something truly incredible must lie within such an immense nothingness? This cultural fascination does more than just entertain. It directly fuels scientific curiosity. The scientist who devotes their career to mapping the cosmic web might have first been captivated by a Star Trek through a fictional void. The line between metaphor and hypothesis often blurs. The idea of a void as a gateway, once pure fantasy, now finds a faint echo in highly speculative but mathematically rigorous theories about the multiverse. Our stories create a cultural vocabulary for cosmic wonder, giving us the language and the emotional framework to even begin grappling with these concepts. They remind us that the journey into the cosmic shadows is not just a technical challenge for astronomers, but a fundamental human pursuit to find our place within the grand and mysterious narrative of the universe. The possibility of life existing within these profound emptinesses forces us to abandon all Earth-centric assumptions. We naturally equate life with sunlight, warmth, and a planet orbiting a star. But the rules of biology might be far more flexible than we ever imagined. Drifting through the cold dark are rogue planets, worlds that have been flung from their solar systems. These cosmic nomads would know no day or night, only an eternal, deep freeze. Their surfaces would be frozen wastelands, but beneath miles of ice, a different story could unfold. Tidal forces from a planet's own rotation or heat, left over from its violent formation, could maintain vast, global subsurface oceans of liquid water. We know this is possible because we see it in our own solar system, on moons like Europa and Enceladus. In those lightless oceans, life would not rely on photosynthesis but on chemosynthesis, drawing energy from chemical reactions, just as the bizarre ecosystems around hydrothermal vents on Earth's ocean floor thrive completely independent of the sun. Could similar biospheres exist in the dark heart of a void, sustained by geothermal warmth and exotic chemistry? The potential for such life is not limited to rogue planets. Some of the most speculative theories propose that life could take forms we cannot even conceive. Could strange particles of dark matter interact in complex ways to form self-replicating structures, a form of biology based not on atoms, but on the universe's most mysterious substance? Or might clouds of complex molecules in the tenuous gas of the void achieve a kind of metabolic process? While these ideas border on science fiction, they serve a vital purpose. They push us to expand our definition of a habitable zone far beyond the narrow band around a star. The true cradle of life might not be a warm, sunny pond, but a dark, icy ocean adrift in the void, or a process we have not yet begun to imagine. The question is no longer just where life could exist, but what life even is. This profound emptiness becomes a lens, a cosmic magnifying glass warping the very fabric of reality. The phenomenon is called gravitational lensing, and it is one of astronomy's most powerful tools. According to Einstein's theory of general relativity, mass curves the space around it. Light traveling in a straight line through that curved space appears to bend from our perspective. We usually see this effect around massive objects like galaxy clusters, where the gravity is so intense it can twist the light from background galaxies into spectacular arcs and rings. But within the cosmic voids where matter is sparse, the effect is far more subtle. Here, the lensing is not caused by a single massive object, but by the collective, diffuse gravity of all the unseen matter within the void, primarily the dark matter that forms its faint scaffold. This creates a weak but measurable distortion in the shapes of millions of galaxies that lie far beyond the void. To our telescopes, those distant galaxies appear ever so slightly stretched and sheared, as if viewed through a faintly warped windowpane. By meticulously measuring this tiny distortion across the vast expanse of a void, astronomers can literally map the distribution of mass within the emptiness itself. They can trace the invisible skeleton of dark matter that our eyes cannot see. This turns the void from a subject of study into a scientific instrument. We are using nothingness to weigh the unseen. What strange anomalies might this technique uncover? Could it reveal clumps of dark matter drifting in isolation, or perhaps detect the faint gravitational tug of a vast number of rogue planets? It might even reveal something more profound, a place where gravity itself behaves differently than our models predict, a potential clue to new physics. The darkness does not hide its secrets, it reveals them through the subtle bending of starlight, guiding us toward a deeper understanding of the cosmos. These faint temperature ripples are a direct message from the universe's infancy. The cosmic microwave background radiation is the oldest light we can observe, a snapshot of the cosmos when it was just 380,000 years old. At that moment, the hot, dense plasma of the early universe cooled enough for atoms to form, releasing a flash of light that has been traveling and cooling ever since, now appearing as a uniform microwave glow. But this glow is not perfectly smooth. It contains tiny fluctuations, hotter and colder spots that differ by mere millionths of a degree. These minute variations are the seeds of all structure. The slightly denser regions, appearing as warmer spots in the CMB, would eventually collapse under gravity to form galaxies and clusters. The cooler spots correspond to the underdense regions, the destined to be voids. This means the blueprint for the vast cosmic voids we see today was imprinted on the universe in its first moments. By studying the specific patterns of these cold spots, cosmologists can trace a direct line from the ancient afterglow to the immense emptiness we observe now. It is a fossil record written in temperature, a cosmic prophecy that has unfolded over nearly 14 billion years. How exactly does a void, billions of years later, affect this ancient light? As the CMB photons travel across the universe toward us, they pass through these vast, empty regions. When a photon enters a void, it must climb out of its gravitational well. Because a void has less matter, its gravity is weaker than the surrounding dense areas. This means the photon loses more energy exiting the void than it gained entering it. This loss of energy stretches the photon's wavelength, making it appear colder to our instruments. This is called the integrated Sachs-Wolf effect, a subtle but measurable imprint that emptiness leaves on the oldest light in the universe. The controversial cold spot in the constellation Eridanus is the prime example. Its existence suggests a profound void along our line of sight, one so large that its gravitational effect on the CMB is detectable. While the exact nature of this void is still debated, its potential connection to the CMB demonstrates how these empty regions are not passive. They actively interact with the fabric of the cosmos, shaping the journey of light across eternity and providing a critical link between the universe's fiery birth and its vast, structured present. Even in the deepest emptiness, an invisible force may be at work. We have mapped the dark matter and pondered the dark energy, but another, more subtle player could be weaving through the cosmic voids: magnetism. The space between galaxies is not a perfect vacuum, and it may be threaded with incredibly faint magnetic fields, remnants from the universe's most violent early epochs. When the first stars and galaxies formed, Their explosive deaths as supernova would have blasted out waves of charged particles, seeding the intergalactic medium with weak magnetic fields. Over billions of years, as the cosmic web formed and voids expanded, these fields could have been stretched and diluted, but perhaps not erased. They are unimaginably weak, billions of times fainter than the magnetic field that wraps our own planet, making them nearly impossible to detect with our current technology. Yet their potential influence is profound. These ghostly fields could act as cosmic guides, shaping the paths of high-energy particles called cosmic rays as they streak across the universe. They might even play a role in preventing the tenuous gas within a void from collapsing under its own gravity, helping to maintain the void's immense emptiness. The greatest mystery is their origin. Could these magnetic fields be entirely explained by those ancient stellar explosions, or does their persistence hint at a more exotic source? Some theories suggest that processes involving dark matter, or even phase transitions in the early universe, could have generated these fields on a truly cosmic scale. To find them, astronomers must look for the faintest of clues, a subtle polarization or a twist in the light from distant radio sources as it passes through the void. Discovering a magnetic field in such an empty place would be a monumental achievement, revealing that even nothingness has a hidden structure, an invisible framework woven into the fabric of space itself. It suggests that the void is not a passive absence, but a dynamic environment where forces we are only beginning to sense are quietly shaping the story of the cosmos. The relentless growth of these cosmic voids is not a static feature but a direct preview of the universe's ultimate fate. As dark energy continues to accelerate the expansion of space, these immense regions of nothingness will grow even larger, their boundaries pushing outward and merging with neighboring voids to form ever more gargantuan supervoids. This is the engine of the Big Freeze, a scenario where the cosmic web itself is stretched and torn apart. The bright filaments of galaxies will be pulled thin, severing the connections between island universes. Within each isolated cluster, star formation will slowly sputter out as the raw materials are locked away, used up, or flung into the deepening dark. The universe will not end in a cataclysm, but in a slow, cold, and silent fade, a descent into a state of near-perfect equilibrium where the average temperature everywhere approaches absolute zero. This is the destiny that the voids are guiding us toward, a future written in their relentless expansion. Yet this prediction hinges on our current understanding of dark energy as a constant force. What if our models are incomplete? Could the properties of dark energy change over time, perhaps weakening or even reversing, leading to a different, unforeseen fate, like a big crunch where the universe collapses back on itself? Or could something even stranger occur? The evolution of these voids is our most sensitive barometer for measuring the true nature of this mysterious force. By meticulously tracking how they grow and change over billions of years, we are essentially reading the final chapters of the universe's story. This cosmic perspective stretches our sense of time to its limit, forcing us to contemplate a timescale so vast that all of human history is less than a single frame in a billion-year movie. It is a humbling reminder that the shadows we study today are not just empty spaces, but the active architects of everything to come, holding the silent, patient clues to the ultimate destiny of all existence. These immense cosmic voids present a profound ethical dilemma that reaches far beyond our current technological grasp. As we develop the capability to one day probe these deepest of cosmic shadows, we must ask ourselves a fundamental question about our role in the universe. Should we treat these regions as pristine wilderness, a form of natural cosmic heritage to be preserved in its untouched state, or are they a new frontier, ripe for exploration and perhaps even utilization? This debate mirrors ongoing conversations here on Earth and within our own solar system regarding planetary protection protocols, which strictly limit how we explore places like Mars to avoid contaminating potential ecosystems. A cosmic void, while seemingly empty, may hold unique and fragile conditions that we do not yet understand. The act of sending a probe, or one day a ship, into such a region could irrevocably alter its natural state, introducing elements, energy, or even biological contaminants from our world into an environment that has been isolated for billions of years. Our curiosity is a powerful driver of discovery, but it must be tempered with a deep sense of responsibility. How do we balance our innate desire to explore and understand with the humility to preserve the unknown for future generations? The answer may lie in developing a new ethic for space, one that views these vast emptinesses not as barren wastelands to be claimed, but as sacred examples of the universe's fundamental nature. They are the blank pages in the cosmic storybook, and we must be thoughtful authors, ensuring that our first footstep into the void is taken with reverence, not just ambition. The stark emptiness of these cosmic voids demands more than just a telescope to comprehend. To truly grasp their nature, we must draw upon the entire spectrum of human knowledge, weaving together insights from physics, philosophy, and even art. Each discipline offers a unique lens through which to view the darkness. Philosophers, for instance, have long grappled with the concept of nothingness, a pursuit that takes on a thrilling new dimension when faced with a 300 million light-year wide example of it. Their inquiries into the meaning of absence and existence provide a crucial framework for the raw data astronomers collect. Meanwhile, the challenge of mapping these immense, invisible structures has pushed mathematicians and data visualization experts to create breathtaking new tools. They transform unimaginable scales and abstract gravitational fields into intricate three-dimensional models and stunning visual maps, turning the void's negative space into a tangible, navigable landscape we can finally begin to explore. This is not a solitary endeavor. The most profound breakthroughs often happen at the intersections where a cosmologist's data meets a computer scientist's algorithm, or an artist's rendering sparks a new question in a physicist's mind. How can a poet's description of emptiness help us understand dark energy? Perhaps the emotional weight of isolation captured in a symphony mirrors the profound solitude of a loner galaxy, offering a different kind of truth about the cosmos. This collaborative, holistic approach is essential. The universe does not respect the artificial boundaries we build between academic departments. The biggest mysteries, like the true nature of these cosmic shadows, refuse to be solved by a single field working alone. They require a united front, a symphony of human curiosity where every instrument, from the equations of mathematics to the intuition of art, plays a vital part in illuminating the dark. Yet this grand exploration is not meant for scientists alone. The profound mysteries hidden within the cosmic shadows belong to everyone, a shared inheritance of wonder that demands to be communicated with clarity and passion. The challenge lies in translating complex concepts like dark energy flows and gravitational lensing into ideas that spark excitement in a public audience. The key is found in powerful human-scale analogies. We do not describe a void as an underdense region in the large-scale structure of the universe. We call it a bubble in the cosmic foam, an ocean of darkness, or a silent desert between the galaxies. These metaphors instantly create a mental image, transforming an abstract astronomical concept into a tangible, almost physical place the imagination can visit. Visual storytelling becomes our most vital tool. Documentaries can use stunning CGI to fly viewers through the Boötes Void, conveying its staggering scale. Planetarium shows can project the intricate web of the cosmic cosmos onto a domed ceiling, letting audiences feel surrounded by the architecture of reality. Even social media platforms offer a powerful stage for sharing these discoveries. A short video animation illustrating how a rogue planet drifts through the eternal night, or a compelling graphic comparing the size of a void to our local galactic neighborhood, can capture the imagination of millions in seconds. The goal is to move beyond just presenting facts and instead foster a genuine sense of shared exploration. By highlighting the unanswered questions, the ongoing debates, and the thrilling potential of a new discovery just over the horizon, we invite the public to become participants in the journey. We are not just telling them about the voids, we are asking them to wonder with us about what might be hiding within them. This approach does more than just educate, it inspires. A child who sees a simulation of the cosmic web might grow up to be the cosmologist who finally detects the warm-hot intergalactic medium. A student captivated by the mystery of dark flow could develop the new algorithm that deciphers its origin. When we turn complex data into relatable stories of adventure and mystery, we ensure that the greatest exploration of all, the quest to understand our universe, continues with renewed passion and purpose for generations to come. Our journey through the cosmic shadows has revealed the profound truth that the universe's greatest secrets are not always written in starlight. These voids are not empty. They are dynamic and influential, filled with the invisible threads of dark matter, the relentless push of dark energy, and the silent drift of rogue worlds. They challenge everything we thought we knew, forcing us to build better telescopes and create smarter algorithms just to glimpse their hidden nature. Each mystery we solve within them seems to unveil two new questions, a perpetual engine driving humanity's oldest and most noble quest, the pursuit of knowledge itself. This exploration redefines our place in the cosmos, reminding us that we are a rare and vibrant spark in an infinite sea of darkness. So as you look up at the night sky, remember that the black spaces between the stars are not voids to be ignored. They are frontiers to be wondered about, full of stories waiting to be told. What do these cosmic shadows make you wonder about our universe? Share your thoughts below, and be sure to subscribe for our next adventure into the unknown, because the universe's greatest stories are often written